Today, we're going to talk about alternating series. So an alternating series has two parts to it. First is the sequence, and the second is this minus 1 to the n called the alternator. And this is where the alternating series gets its name, because this makes the terms in the series alternate between positive and negative. So plotting the partial sums of an alternating series on a graph would look something like this. And notice that as we increase n, the magnitude of the value we're adding or subtracting always decreases, so that it tapers off to some finite sum. And we're going to use that observation to come up with the rules for which an alternating series converges. So again, notice that as we increase in n, the magnitude of the change in the sum decreases. If we look at it stepwise, we can say that a condition for convergence is the n plus 1th term must be less than or equal to the nth term. Notice how unlike a normal series, an alternating series has this or equal to on it. And this is because in a normal series, if we had two of the same value, they would get added to each other, making the sum bigger. But in an alternating series, one is positive and one is negative, so in fact, they would cancel. So all this is saying is that the current term should be less than or equal to the last term. This is a recursive definition. If we look at the entire sequence's behavior, this has to be true for every n. So we can also say that a requirement for convergence is the limit as n goes to infinity of the sequence must be 0. Because of the alternator here, these are the only two conditions that have to be met for an alternating series to converge. Now suppose that you want to find the sum of the alternating series. While we can't compute the infinite sum of this series, we can compute partial sums. And we also know that this nth partial sum is not equal to the actual sum. So this subtraction here will result in some difference we're going to call the alternating series remainder for n terms. So what the alternating series remainder theorem says is that the difference in the actual sum and the nth partial sum is less than or equal to the first neglected term of the sequence. And we can see that this is true by again looking at the graph of the partial sums. So let's assume that this dot here represents the nth partial sum, or our approximation of the series to n terms. So if you notice here, the graph tapers to the horizontal asymptote of the actual sum, meaning as n grows larger, the gap between the partial sums and the actual sums only gets smaller. So the maximum error that can be in this approximation is the effect of the next term in the sequence. And the alternating series remainder theorem is sometimes written like this, where now we have an interval that the actual sum can lie in. The alternator here can do a lot of things to change the behavior of a series. Do you remember this series? This is a very famous divergent series. But if you put an alternator on it, then the limit of the sequence as n goes to infinity is 0, and the n plus 1 term is less than or equal to the nth term. So by the alternating series test, this has to converge. Because of the changes that an alternator can do to the behavior of a series, we have to distinguish between two types of convergence when dealing with them. Here, I've taken the alternator and our sequence and condensed them into one sequence B so that the explanation is a little clearer to see. So if we have the infinite sum of B of n, this is the same thing as the infinite sum of the alternator times A of n. And down here, we have the infinite sum of the absolute value of B of n. So if you remember, the absolute value just takes everything and makes it positive, or it just gets rid of the alternator, like so. So there are two outcomes that can occur in the relationship between these two series. And the first one is, if this with the alternator is convergent, but without it is divergent, then we say the infinite sum of A of n is conditionally convergent because it needs the alternator or the condition to converge. The second outcome that can occur is series 2 is convergent. Then we call the sum of A of n absolutely convergent because it can still converge without the alternator or with an absolute value on it. Notice how in the second outcome, I don't have to talk about series 1 at all. So if the series where we're only adding converges, then this series also has to converge because we're using the same terms, but we're subtracting some, and that drives this to settle on a value a lot faster. Now we're going to use the alternating series test to see if these two series are absolutely convergent, conditionally convergent, or divergent. It's best to check first for absolute convergence because remember, if a series is absolutely convergent, then we don't have to worry about the conditional. So for this first one, I'm going to begin by seeing if this series without the alternator is convergent. So now we have the infinite series of 1 over theta to n. Notice that we can pull this n out to the outside of the fraction, so we have 1/3 to the n. And look, this is a geometric series with our r of 1/3. Since remember, r is less than 1, this is convergent. Since the series without the alternator is convergent, this whole series is absolutely convergent. For the second series, we're going to go ahead in a similar fashion. I'm going to check if this is absolutely convergent. So we have the infinite sum of 1 over n to the 2/5. So if you'll recall, this is a p-series with p equal to 2/5. And remember, since the conditions for a p-series conversion is that p has to be greater than 1. Since this is less than 1, this series is divergent. But now we have to check if this is conditionally convergent. And recall that these are the conditions for alternating series convergence. I have the limit as n goes to infinity of 1 over n to the 2/5. And so we see that as n grows to infinity, this fraction goes to 1 over infinity to the 2/5, which is 1 over infinity, which goes to 0, satisfying our first requirement. Secondly, we have to see if this relationship is true. Looking at the denominators, we see that each of them is something to the 2/5. But notice that on this side, for every n, this will always be a bigger term to the 2/5, meaning this denominator will always be bigger than this denominator. And since they're both dividing 1, this is dividing 1 into more pieces. So this relationship is true. So because this series diverged without the alternator but converged with the alternator, we say this is conditionally convergent. And that's how you use the alternating series test.